Hello, welcome to the first episode of Joyful University. My name is Joy, just like in the dictionary, and I'll be making this playlist to help students who are applying to study engineering, physics, maths, or computer science. If you're not a uni applicant, but you are interested in problem solving, then I promise that you have stumbled on the right channel. I'm an engineering student myself, so as well as teaching, I'd hope to learn a few things along the way, and stay tuned for my Joyful Engineering playlist because I'll be performing scientific experiments and hopefully building a robot in the future too. But today we're going to be focusing on a problem based on maths and computer science. Imagine you work for Casio. How would you write a program that returns the probability of a normally distributed variable? So let's start off by mapping out our problem. We'll draw our bell curve, which is our normal distribution, and we'll consider some variable x. Now, it'll have two parameters that define the variable x. Its mean mu and its variance sigma squared. And there'll be an instance when the mean mu is actually 0 and the standard deviation is 1. And when we have that instance, it's our normal distribution for the variable z. And the special thing about this curve is that the area underneath that curve is the probability that an event will occur underneath that region. And hence that's why we call it a probability density function. So let's imagine we wanted to find the probability of our variable z being in between 0 and 1. That would be our shaded region. But let's say we wanted to find the probability that our variable z is less than some x value. That would be the region shaded all the way from negative infinity. So we can take the definite integral from negative infinity to our variable x of our function y with respect to x, and that gives us the area. And remember that for this type of function, the area is going to be that probability. Our equation is going to look a little bit scary, but bear with me, we'll simplify it in a minute. So it's y equals 1 over sigma times the square root of 2 pi. But 1 over root 2 pi is just some constant we can call k. And then we multiply that by e to the power of minus half times x minus mu over sigma all squared. But the exponent of e can just be called some variable z. And if we call that z and k, we can simplify our equation into a form which is y equals ke to the z over sigma. Now, it's very difficult to compute an integral like this, so we're going to be using something called the trapezium rule. So what we do is we split our function into tiny strips made of little trapeziums, and we have an x value that goes to some y value, and we have an x2 value that goes to a y2 value. So let's consider the change in x. We can call that dx. We can say that dx equals x2 minus x. Now, considering our trapezium rule, we know that the area equals the height divided by 2 multiplied by the sum of the two sides. So we can just simply implement our other variables into this formula where the change in area we can call dA, and the height is dx, and the two sides are respectively y and y2. Also, it's going to be important to note for our algorithm in the future that we can rearrange our equation for dx such that x2 equals dx plus x. And what this means is that the x2 value is just the previous x value incremented by the change in x. I'm going to be solving this problem in the C++ language, which I self-taught, so don't worry if you don't know it, but I recommend a website that I used called SoloLearn. So now we know how to find the area for one strip. We realize to find the area under our graph, we just have many strips up to our x value. We'll call that capital X. So we have the area for the first strip plus the second strip all the way up until the nth strip. So what we can say is that the cumulative area is the sum of all of the areas for all of those individual strips. And in computing, we can say that the cumulative area is incremented by the change in area. So that's written as AC plus equals dA. The last thing we're going to figure out is the exit condition for our iterative loop. So remember, capital X is our user input, and we want our last iteration to fall on that value of capital X. And remember, each time we are incrementing by the change in x, dx. So if we want to be one iteration away and land on x, capital X, we'd say while x2 is less than capital X, take away one iteration. And remember that one iteration is dx. So while x2 is less than capital X minus dx, we run our iterative loop. One of the things that's quite important to consider when making any sort of program like this is how to produce an accurate set of results. So we want to start off with a large negative number, say -4, because the cumulative area that's less than -4 is so small that it can practically be called 0. Also, for accuracy, we want a small interval, so let the change in x be 0.01. You can have an even smaller interval, but remember that's going to run more iterations and increase the runtime of our program. Okay, so I can imagine that was a lot of information in a small amount of time, but if you're having any issues, feel free to ask me a question in the comments, and we can finally start coding now. So firstly, let's define our constant variables. We're going to have our change in x, which is 0.01, Euler's number, and the square root of 1 over 2 pi, which is 0.39, and so on. Then we're going to start our loop at x equals -4, and our cumulative area must be 0. Remember that we said that x2 equals x plus the change in x, and the rest of the values are just numbers and letters that we'd used before. Also, it's important to include the C math library so we can use functions such as power of, and we can use that to write our equation. To allow for user input, we say that C in x. Then we run a while loop with our exit condition that we mentioned previously. And as we run our while loop, we say that x is incremented by the change in x. And we bring up our formula for z, and we say that z equals -12 x minus mu over sigma squared. In other words, x minus mu over sigma to the power of 2. And finally, we can bring up our formula for y, which is y equals k times e to the power of z over sigma. So now we can just copy and paste this code and say that x, y, and z is replaced with x2, y2, and z2. We can do this because in our variables we declared that x2 was offset by one iteration. All we need to do now is use our formula for the trapezium rule, and we say that the cumulative area AC is incremented by the change in area dA. And then we can just say print or cout AC. For the moment of truth, we'll run our program and we'll test it with the input -1. We can see that we get a decimal number, but we can make this look much neater if we include IO manipulation. And then we can go to our print function and we can say standard cout, standard set precision to 4, and what this will do is print to 4 significant figures. Then we can manipulate this and we can add some text to say probability z is less than our user input x, then multiply our area by 100 and put percentage in text at the end and then end the line. And if we run this program again, we should get a nice coherent sentence this time. If we run this again, we see that we get 15.86% printed, and for large negative numbers, we get a probability of 0, and for large positive numbers, we get a probability of 100%. Now, we can check this against an online calculator that I use called Desmos, link in the description, and it does the calculation, and we do see that our answer is indeed 15.86%. Thank you so much for watching, and I really hope that you learned something new from this episode. Stay tuned for the next episode, which is going to be on making tea with differential equations. Until then, stay joyful!